We're tackling shortest unsorted continuous subarray here, and we're going to try and solve it with minimum complexities of on time and O1 space. In our problem statement, we're given an integer array nums and need to find a continuous subarray such that if we sort this subarray into non-decreasing order, the entire array will also be sorted in non-decreasing order. We want to determine the length of the shortest subarray that satisfies this condition. So, we have four possible methods to solve this. They are A. Sorting plus greedy, B. Linear scan, C. Hash table, or D. Stack. I'm going to pause for a couple of seconds while you make your choice. So, for those of you who were able to get it, congratulations. And for those of you who just want to see some code, the answer is B. Linear scanning. The brute force approach here would be to check every possible subarray to see if it's sorted. Obviously, this isn't really that viable, but it's included here just for posterity. In our optimized solution, which utilizes linear scanning, we can find our shortest unsorted continuous subarray. By iterating through the array from left to right, and then once more from right to left, we can identify the leftmost and rightmost positions where our array is not in non-decreasing order. Finally, the length of the subarray between these two positions, right and left, is what we're looking for. Of course, if we don't find anything like that, we'll just be returning 0. So, let's take a look again at how this works. In this case, we will make reference to the examples given by LeetCode as well. So, first of all, we're initializing left and right variables to -1. These represent the initial state where we haven't found any unsorted positions yet. We then initialize sz, which is the size of our nums array, and set the max value variable to the first element of our array. After that, we iterate through the array from left to right, here from the second element at index equals 1, all the way through to the last. For each element, we update max value to the maximum value between the current element and max value. However, if the current element is not equal to max value, it means the array is not sorted in non-decreasing order at this position. So, we update right to the current index. So, I hope you can see how this is going to work with these arrays here. So, in example 2, which is completely sorted, max value will start out at 1, increase to 2, then go to 3, then go to 4, and there'll never be a case where max value does not equal nums I. So, right is going to remain at -1, and eventually we're going to be returning 0. However, with the array in example 1, you can see that while max value won't change, won't be different for the first two, it will differ here at 4. Then it will differ again at 9. And we'll end up with right being equal to 0, 1, 2, 3, 4, 5. Conversely, let's take a look at how min value is going to work. So min value is initialized to the last element in the array. We then iterate from right to left, here starting from the second to last element and going through to the first. Once again, we're going to update min value to the minimum value between the current element and min value. Again, if the current element does not equal min value, it means the array is not sorted in non-decreasing order at this position, so we update left to the current index. So, once again, looking at our examples, you can see in example 2, it really doesn't matter actually, but we'd start with the min value being 4, it would go down all the way to 1, and there'd never be a discrepancy between min value and nums I, so left would again remain at -1. However, for example 1, min value would start at 15, jump down to 9 and be fine, but then at 10 there'd be a discrepancy, so left would initially be 4 here, and then eventually we'd have another discrepancy again here at 6. So left would end up being 1 in this case. I hope you can see how that works. In any case, after we've iterated from left to right, comparing the max value to the element, and from right to left, comparing the min value to the element, if right remains at -1 after the iterations, it means the array is already sorted, so we're returning 0. Otherwise, we're going to return the length of the subarray, and that's going to be basically the length of the subarray between right and left, adding 1 to it. So in the case of example 1, we'd be taking 5 minus 1 plus 1, which gives us the output of 5. And that's our shortest unsorted continuous subarray. Okay, now for a better visual solution, I can recommend the algorithms course, which is in the description to this video. And that's it. We're going to have one more look at the problem and potential methods here. And we can use linear scanning to solve shortest unsorted continuous subarray. We've got quite a lengthy explanation as to why here. And if you still need help, you can check out the code in C++, Python, and Java as well. So that's everything. Thanks very much for watching. And if you're following the algorithms pack in the learning mode of Coding Card Sharp, the next problem is going to be most profit assigning work. Hope to see you then.